Okay, welcome to our video lecture here on the conservation of momentum. Conservation laws, we're going to find out that there are a lot of them in science. There's three big ones. One of them is the conservation of mass, and that's mainly studied in high school chemistry. Physics, we focus on the conservation of momentum and the conservation of energy. But in science, what does it mean for something to be conserved? It means that something is not changing over time. So and we usually say a conservation law with something like it's never going to be created or destroyed. So in chemistry, when we study balancing equations and stoichiometry, we'd say that mass is never created or destroyed, or atoms are never created or destroyed. Momentum and energy are going to be the same thing for physics. Whatever momentum we start with in a certain system, or how much energy we start with in a system, won't change. And that's what we're going to study then today. Calculus, for some of you may be taking calculus, a conserved quantity in calculus would mean that the derivative with respect to time would be zero. It means that there's no change. So we're going to take a look at the conservation of momentum, and remember what that means then today is that momentum is never created or destroyed. Whatever we start with, we have to end with. A couple things we have to remember then to keep in mind from our recently studied material are a few things. So we can understand the derivation of the conservation of momentum. We do want to know about momentum itself and changes of momentum. Remember, changes of momentum were given by delta P, and we could write that a couple of different ways, m times delta V, and we could expand that out and say, well, that's m times final velocity minus m times initial velocity. That's a change in momentum. We also studied the impulse momentum theorem. That says that a change in momentum is equal to the impulse imparted on an object. Another way to think about that, right, is how do you want to change an object's momentum? You have to exert a force. It's a push or a pull, and that push or a pull needs to be applied for some amount of time. So F times T was called the impulse, and in physics that causes a change in momentum. They're equal to one another. So we're going to quickly derive where this conservation of momentum comes from. We're going to come up with a master conservation of momentum equation that would describe and predict almost any type of collision or interaction that we could imagine between two or more objects. Let's think about two cars colliding. This being Tahoe, they probably would be Subarus, right? So Subaru A and Subaru B. You can imagine, and we're going to make it easy, Subaru A is traveling at one speed in this direction, the same Subaru B moving at the same speed in the opposite direction, and bam, they collide. We want to be able to analyze what would happen if this does happen, and then ultimately have an equation that would tell us, well, what if they're different size cars, maybe an SUV and a compact, and what if they're going different speeds? This one equation that we're going to come up with will be able to do all of that. So let's go ahead and begin. Let's go back to our first section. If you remember, we dealt with Newton's third law, which we'll abbreviate the cool way here, right? N3L, says this, that when they collide, there will be a force on A. So we wrote them this way, we subscripted B on A. That's the force of car B pushing A to the left. And we learned then by Newton's third law, forces come in pairs and they act on different objects. So this vector might represent the push or the force of A on B, right? And they are equal and opposite. So from our forces unit, we would classify that as an action-reaction pair. Just so we don't get carried away with the subscripts, what I'm going to do is I'm just going to refer to these by the forces on the object. So I'm just going to get rid of the subscripts here and just simplify it. This is going to be, we're just going to call that's the force on car A, and this will be the force on car B. And we'll do it a little bit mathematically here. What that means is F of A is in the opposite direction to F of B. Usually left is the negative direction, so we could say this, negative FA equals FB. And remember, these are vectors. And that's just a restatement of Newton's third law. Forces occur in pair, they're equal and opposite in direction, same magnitude, and they occur on two separate objects, cars A and B. Where we could go next then is we could realize that we could also talk about the impulses imparted to each of these cars from the other car, and we would realize that when they crash, they're in contact for the same amount of time, right? So delta t in this equation would be the same. That should make sense, right? It's impossible for car B to touch car A any longer than car A is touching B. So they're pushing each other for the same amount of time. This should look familiar, right? This right here, F times delta T, that's something from last unit that we called the impulse. And if you remember, an impulse produces a change in momentum. So another way I could write this out using the impulse momentum theorem would be this. The change in momentum of car A, the negative change of momentum, would be equal to the change of momentum of car B. So all I'm going to do next is just expand that out, and we're going to come up with the law of conservation of momentum. Okay, so here we go. Delta PA, so I'm going to work on this side first. Delta PA, and expand it out. So what am I going to get? I'm going to get a negative, lots of subscripts here, mass of car A, velocity of car A final, and that negative sign is going to distribute through, so I'm going to get a plus mass of car A, velocity car A, initial. Right? That's all we're doing is expanding that out. The other side then, I'm going to expand this one out. Delta PB. This is going to be the mass of B times the velocity of B final minus the mass of B times the velocity of B initial. The last step is typically we want to isolate the initials and the finals on one side, so that's what I'm going to do here. I'm going to put the initials on the left side of the equation, so I'm going to get mass of A VAI plus, add this side to the other side, mass of B VBI. We'll put the finals on the right side of the equation. So I'm going to add this over here. MAVAF plus this one here, MBVBF. This is it, guys. This is the master equation for the law of conservation of momentum. And what it says is momentum is not created or destroyed, but it says in mathematical form, right? This is the total initial momentum. So the momentum before the interaction, total initial momentum. And the F's here signify that this is the total final momentum. And this would be the total momentum of a system or after an interaction or a collision. So this master equation, this idea of the conservation of momentum, is super powerful, super important to physics. There are some stipulations for it. The system must be closed, and what that means when we first start studying physics is that means that we cannot change mass. So while we're talking about this, there'd be no change in the mass of the two cars or whatever's colliding or interacting. And it also means that the system is isolated, and that means that there is no outside force. So if we talk about two cars colliding or something like that, what we have to assume is that they sort of drift into one another. The cars might be in neutral. No one has their foot on the gas or the foot on the brake while they're interacting, so they're just kind of running into each other on their own inertia. But this is, again, this is the conservation of momentum. And it says something, even though there's a lot of variables, it says something pretty simple but profound. It says that the total momentum before, sometimes the total is given by the summation symbol, sigma. Total momentum before, which is the total momentum initially, equals the total momentum finally. That's all we're saying. So what I'm going to show you now is how to set up the three typical problems in the conservation of momentum idea, and with no numbers, and just get you prepped for doing some numerics later. Okay, this would be a problem that's a classification. Typically it's called a recoil or an explosion problem. And it's kind of the opposite of a collision. Two things are going to start off, you can think of as one object, and they're going to become two separate objects afterwards. So these safety-conscious skaters with their helmets and knee pads, they start off stationary together and they move away as separate objects in two different directions. So that's a recoil. Another way that you might want to think about it is, if anyone's ever shot a gun, it recoils. The bullet goes one way, the gun pushes back in the other direction. And those are the types of problems that we would see in this case. So let's take a look at how we'd set this problem up. Let's look at them before, and that means initial, right? Well, they're standing still. Even though they both have mass, 48 kilograms and 40 kilograms, their velocity is 0. So that means the total momentum to start with is 0. And the units, which as I forgot about, are going to be kilogram meters per second, mass times velocity, right? But let's take a look at afterwards. Someone's moving in one direction and the other is moving in the other direction, in the opposite direction. So if I put the numbers in that are given to us, it should make sense then in this case. Let's call the boy A and the girl B. So we have a mass for the boy of 48 kilograms. He's moving to the left, so I'm going to say that's negative 2.5 meters per second velocity. And then we're going to add to that the girl's velocity, the girl's momentum rather, which is 40 kilograms of mass times 3 meters per second. And she's moving to the right, we'll say that's positive. So what do we have? A quick simple calculation will tell us that this does indeed support the law of conservation of mass in this case. The boy's momentum after the interaction, or the push in this case, is negative 120 kilogram meters per second. The girl's momentum afterwards is positive 120 kilogram meters per second. Remember, they started off with a total momentum initially of 0 kilogram meters per second. So indeed, this does show the conservation of momentum. And again, what's typical of a recoil problem? One object here becoming two. So we're always going to have, if we start with 0 momentum, one object's going to have negative to compensate for the other object's positive momentum. Here's another real common class of conservation of momentum problems. Two train cars colliding and hooking up here and becoming one more massive object and moving away together. Let's take a look at how the equation, this master equation, would look in this case. We'll call the red car car A and the blue car car B. And then when they're stuck together, they're A plus B, one big mass here in this case. So we have the mass of A plus the velocity, or times the velocity of A. Let's look at B. B is sitting still. It's not moving at all to begin with. So it's just sitting there waiting to get hit. That means that its velocity is 0. That means its momentum is 0 in this case. Afterwards, they hook up and they're stuck together, so they have to move at one final velocity. So if these are the same, we could factor that out and we get an expression that looks like this. MA plus MB. Okay, so let's see what we have here. We're going to take a mass of A, 30,000 kilograms, and multiply it by 10 meters per second to get its momentum. That's 300,000 kilogram meters per second, plus the 0 momentum of car B initially. Afterwards, what's going to happen? Both of these things together, since they're both the same mass, will have 600,000 kilograms of mass. How fast will they be going in this case? Well, they would have to be going 5 meters per second. That's what we're solving for, is that VF. But again, we can see how momentum is conserved here in this case. That would give us 300,000 kilogram meters per second. And one of the things I'm just realizing here, it's not 600,000, dummy. It's 60,000. So 60,000 times 5 would be that value, right? That's the mistake I made. They're each 30,000 kilograms, so the total mass would be 60,000, not 600,000. But we do show that momentum is conserved in this case. 300,000 kilogram meters per second. And the last type of problem that we do, maybe if you have to think about being the hardest one, it doesn't simplify in this case, but as two objects are colliding, maybe like bumper cars, they don't stick together, they don't push off each other, so they never function as one larger mass. moving at one velocity, they stay separate. So imagine car B is moving in here, and bam, A is sent off this way, but car B is still moving a little bit afterwards. In this case, we would have to keep the full-blown conservation of momentum equation, because we would have non-zero velocities for both cars before and after. So depending on the problem, we have to use all of those terms in there.